So we're going to do a review for exam 1 today. And are there any of these specific problems that you want to attack first?
Mine was 29.
29?
Yeah.
Okay. Let's see. Go down. Would that be the phase diagram? Okay.
It's probably like common knowledge, but my head cannot wrap around it for some reason.
Okay. Okay. Yeah. Okay. So we'll do 29 first. And this is chapter 10 easy, I think, isn't it? Chapter 10. I believe. For some reason, this handout has I've started renumbering each time. I don't know why. Let me be sure that's correct. Yep. Okay, so we'll get 29 and be sure so that that's covered, and then I'll go back and we'll pick up some highlight. That happens to be one of the highlighted ones. Okay, so we're given this phase diagram, and in this case, we have temperature on this scale and pressure on this scale. And we're working from here to here, then there to there. Then this one goes negative slope. Okay. You're not told, let's see, they do give us this must be in atmospheres. That's the only thing that makes sense. And they've got one over here, like that's X, position A. Okay, I think I get everything on there now. And that's where that line ends. Okay. These types of phase diagrams are arranged in such a way that you can be pretty sure that this is the gas section, this is the liquid section, and this is the solid section. So at these pressures and these temperatures, you got solid, liquid, gas. The lines are designate combinations of pressure and temperature where you have both phases at the same time. All right, so if we're right here, we've got liquid and gas together. Right here, we got solid and liquid together. Here, we got solid and gas together. If you're right here, you got all three together. That's the triple point. Okay. So what's the question? We have to pick. Which of the following statements is false? Okay, first one, the solid has a higher density than the liquid. All right. This is kind of a tricky question. And that statement is false. And here's the reason why. The only phase diagram that I know of that gives you a negative solid liquid slope is water. And we know that the solid for water, ice, is less dense than the liquid. So that's why A is false, because that's probably water. That's probably the worst statement in there for trying to figure it out. The other should be true. At some constant temperature, the gaseous substance can be compressed into a solid and then into a liquid. So if we go gas, at this temperature, we can go from gas to solid to liquid as we compress it. That's true. C, when phase A is compressed at constant temperature at point X. No change is observed. That's true, because we're beyond the point of the critical point. So all this region out here, we cannot distinguish phases at all. D, when heated at 1 atmosphere, so we stay here and we heat it at 1 atmosphere, this substance will first melt, then boil. Yep. It goes through solid, liquid, gas. That's true. And then E is one of those squirrely ones. And that's actually none of the above statements is false. This one's false too. So you got 2 false statements in there. Yeah. That's a error in the questioning. Okay, so that was 29. Mark that one, 29. Got that one out of the way. So let's go back to the top, unless you have another one. Yeah, that's understandable. All right, so now we're back to 1. Which of the following should have the lowest boiling point? When we're talking about boiling points and melting points, the thing that determines those temperatures is intermolecular forces. What's attracting the molecules together? And if you want the lowest boiling point, you want the weakest attractions. So if we look at ion, those are the highest boiling points. Then we have dipole, and we can have dipole, or dipole ion. And then the next weakest is London dispersions. So if we're looking for the lowest boiling point, we want something that only has access to London dispersion. It's not polar, it's not ionic. Sodium sulfate is ionic, right? So it counts that one out. HF is extremely polar. Ammonia is also a polar substance, right, because of its shape. And water is extremely polar, so the only one that's left is nitrogen. And if we look at the Lewis structure of nitrogen, we find that it's nonpolar, so it only has access to these. That's why D is the answer. Okay. And now 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? All right. We got a water molecule here. That. Which direction is the polarity? Well, individual bonds are polar in that direction. And the overall molecule is that direction. So that gives this end of the molecule a slight negative charge and this end a slight positive charge. But that's overall. When you actually form the intermolecular bond, you don't line them up like this. Right? You still have to depend on the polarity of the bond and what it does to each of the atoms. So each one of these is like that, and to balance, be like that. So when they form these hydrogen bonds, you've got the oxygen from one lined up with the hydrogen of the other one. Okay. And for that, the answer would be B. Hydrogen from one molecule and oxygen from the other. Yeah, that could be a point of confusion when we talk about overall polarity versus polar bonds. Okay. C is referencing these three diagrams. So the first one we see is difluorine. Difluorine. You know, that doesn't make any sense. Unless those delta negatives and positives are London dispersions, because difluorine is nonpolar. And then Roman numeral 2 is ammonia molecules, and Roman numeral 3 is hydrogen chlorides. Okay, so question 4 focuses on the last one. The hydrogen chloride. Now we have to assume the way it's set up that this hydrogen chloride is a gas. It's not dissolved in water. Then it would be hydrochloric acid. Which of the following statements are incorrect concerning drawing 3? Okay. Let's see. A says electrostatic interactions exist between the molecules. Yeah, that's true for any molecule. We're looking for the false one. The molecules find the best compromise between attraction and repulsion. That is also true. Let's see. C, these molecules exhibit ionic bonding. No. This is a covalent bond between hydrogen and chlorine. It just so happens that the bond is polar. So there's a false one right there. So D and E should be, well, then we got another, did it again. OCS exhibits this type of interaction. Yes. If we do this and we do the Lewis structure, then we have, let's see, oxygen is 6, 4, and 6. So that's 16 electrons. We have 2, 4. That's 12 left over. 2, 4, 6, 8, 10, 12. And then we have to form the lowest formal charge will probably be a double bond on that side and a double on this side. All right, so we've got polar bonds there, but which one is more polar? This one. That one is more polar. So we tend to have a negative on this side and actually a positive here and a slight negative there. But this one, let's do that. Makes this one, this end is more negative than that end. So yes, it will exhibit those types of interactions. And then he says 2 of the above statements are incorrect. So this one's false. And there we go again. All right, so we've got a problem with generating logical questioning. Somebody probably hired a graduate student to put these questions together. Okay, which best explains the following trend? So we're looking at noble gases in order from top to bottom. Okay, and we're finding that the boiling point increases from top to bottom. This is one case where we absolutely certain that polarity, fixed polarity, that there are no dipole moments in these because it's just one atom, right? And they have complete octets. They have complete energy shells. They're orbitals. So the only possibility that can explain this increase in boiling point is difference in size. which means as the size increases, the London dispersion forces increase. And it's very simple because this is a bigger atom than this one, than this one, than this one, than this one. You have more volume for the electrons to shift around. Right? They're always in motion. So we have the opportunity for moving to one side, those electrons, and influencing their neighbors the same way that London dispersion have been explained for molecules works for these atoms too. So A, London dispersion forces explains the trend. Okay. Number 7. Which of the following compounds has the lowest viscosity? Okay, we're looking for the lowest viscosity. So what's the relationship between intermolecular forces and viscosity? As the intermolecular forces increase, the viscosity increases because we're holding those molecules together with stronger forces and they don't want to flow. So which one has the lowest viscosity? In other words, which one has the lowest intermolecular force attraction? And there again, we're looking for differences of dipole versus ion versus dipole versus London dispersion. And there again, we have nitrogen gas would have the lowest viscosity. It may seem strange. We think of viscosity in terms of liquids usually, but you can measure the viscosity of a gas. And most gases are very low to begin with, but nitrogen gas is extremely low because it doesn't have access to anything but London dispersion forces. I'm just speculating that 25, 26, 27 carbon aliphatic hydrocarbon looks like grease. So it's going to have probably the highest viscosity. And it's due to two things. If it is grease, then it's due to London dispersion forces because it's a big molecule. You can have lots of attractions between molecules that are side by side. The other thing that we haven't talked about much is entanglement. These big molecules, they can go all different directions, especially if they're nothing but single bonds. And that's what this one is, because things can rotate around single bonds. You could get that thing rotating around where it's just a clump of itself. So entanglement enters in there also, but that really wasn't a focus of our discussion in each chapters. That's just in case you want to amaze your friends at parties. Number 8, when a nonpolar liquid displays a convex meniscus. So when we say meniscus, the liquid must be inside a container of some kind. And a convex meniscus is like that. Okay. So what does that mean in terms of cohesive and adhesive forces? The cohesive forces in here are greater than the adhesive forces that are displayed right here between the liquid and the walls of the tube. So B is a good answer. Cohesive forces are stronger than adhesive forces, right? The others, low surface, no, it doesn't have a low surface tension. Actually, these guys have a very, very high surface tension. Okay, that's good enough for that one. Right. Go down to number 9. I think I'm gonna graduate to a fresh marker. Number 9. Which substance can be described as cations bonded together by mobile electrons? Okay, this concept goes back to the early theories of metals, how metal atoms attract one another. Right, so we need a metal, some metal atoms, right? So there'd be positive nuclei, and then it has electrons everywhere, just scattered around. This theory probably developed before we had an understanding of the structure of the atom. So, which one of those is a metal? Oh, the first one, silver. Yeah, silver's a good one. We didn't, the metallic bond then developed once we started understanding how atoms were built. And we really didn't get a good explanation for how metals bond until we got to molecular orbital theory. Okay, number 10. Which of the following statements about steel is false? Okay. So what is steel? Steel is an alloy of iron plus carbon. And then you can add some other stuff, but that is essential. You have to have iron and some carbon. Usually 0.5% by mass or less will give you steel. Okay, so number 10, we're looking for the false statement. Contains carbon atoms in the holes of its iron crystals. Yes, it's an interstitial alloy. So the carbon atoms are so small, they fit between in the spaces, the voids that we discussed, the voids between the iron atoms. That's where the carbon goes. So that one is true. Then the presence of carbon-iron bonds in the alloy make the steel harder and stronger than pure iron. Yes. They don't just sit in those spaces. They're actually bonded to the iron. Pure iron is relatively soft and ductile because it lacks directional bonding. You can say that about most metals. They're relatively soft and ductile because they don't have directional bonding. They don't have it. And when we say directional bonding, I usually think of covalent bonds because they're directed between two atoms or more atoms. Whereas undirectional bonding is like, well, like the electron C model. But that idea carries over into metallic bonds that we describe in molecular orbitals too. So that one's true also. The amount of carbon directly affects the properties of steel. Oh, yes. Sure does. So all of these are true. There's a whole lot more to characterizing steels than just these concepts. These are basic concepts, but there a whole lot more goes into it. I mean, there's you can have the same composition of carbon and iron and other impurities that you want to add, like manganese, for instance. Same composition, and the way you treat it, heat treat it, and cool it, determines the arrangement of crystal structure, kind of a major, actually larger
crystals and how they interact with one another. So that's why steel is such an integral part of modern society, because it can be tailored at the molecular level to give us the properties we want. In fact, now cars, automobiles are being built with two things: plastics and high strength steels. These steels that they're making now for our cars, you can get for less weight, you can get the same strength. Let's see. 11. Which of the following statements is true about P-type silicon? All right. So if we want P-type silicon, that means we need an overall deficiency in electrons. In order to get that, we need to substitute for these silicons in this matrix. We need to substitute something that has fewer valence electrons than silicon, which would be to the left of silicon in the periodic table. So something like boron is often used. Gallium can be used. Indium. Boron is very common for P-type. Okay, so let's look at the question. Which of the following is true about P-type? Is produced by doping silicon with phosphorus or arsenic? Oh, wrong direction. So A is false. We're moving to the right. Those are N-type semiconductors. Protons are the mobile charge carriers. That's also false. Protons do not move. They stay in the nucleus, and that's where they identify the atom, so they can't move. It does not conduct electricity as well as pure silicon. That's also false. It conducts electricity better than silicon because we have this deficiency. We have the ability to move either electrons, or in this case, the positive holes. Actually, that's a conceptual. What we're trying to do is make it easier to describe what's happening. So we say the holes move, but actually it's electron move. So electron moves this way, the hole moves that way. Yeah. Okay, so none of them are true. That's E. Okay. Number 14. We're still chapter 10 easy. A solid crystal of sodium chloride is. Okay. If we have sodium chloride in the solid form, it's in an array, a crystal matrix of positive and negative ions. And this goes in 3 dimensions. It goes in the board, now the board also. So this solid crystal then is it soft or hard? It's hard, because those ions are locked in place. They cannot move. So it's hard. Right? That limits our answer to B or D. So we can ignore the others and go straight to B and D. High melting point, yes. Melting point, very high. So it could be either one of those again. Then if we look at the difference, good electrical conductor, poor electrical conductor. It has poor electrical conductivity. But what defines conductivity? The ability for charges to move.
I look at it this way. If you've got something, a substance here, doesn't matter what it is, yet, and you attach a battery to it, all right? So we got our battery here. And then we have a light bulb here. Right? Okay. We have to have a circuit. In order for electrical current to move, it has to be a complete circuit. So if we break the circuit here, we get no light. That's an insulator. If we have a conductor here, then we get current moving, and we designate it with an I. And we get current moving, and then we get light. Okay, so if this is sodium chloride solid, do we have the opportunity for charges to move? No, they are locked in place. It's like this crystal. They are locked, they cannot move. So D is our best answer because sodium chloride is a poor electrical conductor when it is solid. Now, how could we get sodium chloride to be a conductor? Well, there are bonds holding these things together, right? Ionic bonds. We need to break those bonds. And the easiest way to do that is to heat it up, melt it, right? Go to over 1,000 degrees and turn it into a liquid. And if you do that and your electrodes survive, then you can get current through that because now the charges can move and they can carry that current across to the other side. Or we can put it in solution. Right? Just put it in water. Water's an insulator. Water does not carry charge at low voltage. I'll explain why I said that in a minute. But once you get sodium chloride in solution, the sodium ions and the chloride ions now are hydrated and they're able to move. They're in solution. So sodium chloride aqueous solution is a conductor. Now, why did I say water is an insulator? Well, the water molecules have slight charges, but they're not the kind of charge that can convey current across pure water unless you have extremely high voltage. High voltage adds energy to water and it ionizes it. And then it can move. So that's why they say in a lightning storm, if you're out playing around a golf, right, lay down in a ditch. Right? Don't stand in a puddle of water. Unless that ditch has water in it, then you want to because the voltages of a lightning strike will cause water to be a conductor. I don't know if I told you this, the class this before. When I was in high school, I was one of the poor kids. I was a teacher's kid at a private school. So all I had to do was buy my books and a uniform. And there were a few of us like that. The rest of them were rich kids. So they had cabins in the woods and they had summer homes and all kinds of stuff like that. And the story is that one of my classmates had gone to the family's cabin by herself for the weekend. And she was taking a bath. And there was a lightning storm that came through. Well, she would have been okay, except that she was talking on a phone. Back then, we didn't have cell phones. They were all landlines. So she had a perfect conductor next to her ear going to that wire outside. Lightning struck that wire, came down through her, through the water, and ended her career. Yeah, stopped her heart. So there's a lesson in physics there, but there's also a lesson in philosophy, right? You can't take it with you, no matter how rich you are. Okay. A lot of the rich kids were really well centered. They had good parents. but some of them kind of went off the deep end.
Which of the following has the highest melting temperature? What we're looking for here is the one with the strongest forces holding those parts together, and you're looking at ionic compounds. They will have the highest melting temperature. And the only one there that I see in that list that's ionic is magnesium fluoride. Right. Yeah, the rest of them are molecular. Magnesium fluoride, in fact, has, well, magnesium is a 2+ charge, fluorine is a -1 charge. So we have two of them. These ions are relatively small, actually. So we're concentrating that charge into a small area, which increases its coulombic forces. Right. So magnesium fluoride would have a higher melting point than, say, calcium chloride, because those are bigger ions. Spread the same charge over a larger area. It reduces the coulombic attraction. But to answer this question, magnesium fluoride would have the highest melting point. Okay, 16. Which of these statements is false? All right. A, B, C, D, and E. Diamond is a covalent crystal. Yeah. In fact, if there are no flaws, that diamond on your ring, on your finger, is a single molecule. That's true. The size of the unit cell lithium and cesium is the same. No, that's false. The reason being, lithium is much, much smaller than cesium. So even if they have the same type of unit cell, like, let's see, simple cubic, I think, the alkali metals, they're one of the few elements in the table that use the simple cubic. So lithium is a lot smaller. You can make a smaller cube than you can with cesium. So that's our false one. And in the interest of time, I'm going to call it right there. Because even though we have some extra time, it's going to run out quicker than I think. So I'm going to move on to 17. How would you expect the melting point of carbon tetrachloride to compare to that of sodium chloride? Well, it'd be lower, right? Sodium chloride is an ionic compound. Carbon tetrachloride is a non-polar covalent compound. So the melting point will be lower. So A says it should be lower because sodium chloride forms an extended ionic crystal lattice where carbon tetrachloride is covalently bonded small molecule. That's a true statement. Yeah, A is true. Now, do we have any squirrely ones down there? No. They're not similar for B. Should be higher because of the bonds are stronger? No. The intramolecular bonds for carbon tetrachloride are probably stronger than the ionic bonds between sodium and chlorine. I don't know that for sure. They may be, they may not be. They might be pretty close to each other. But when we're talking about melting points, those are intermolecular forces between molecules or between ions. Right? So with that being said, A is your best answer. Let's see, 19 and 20. At normal atmospheric pressure and temperature of 0 degrees C, which phase of water can exist? If we got normal atmospheric pressure, well, we're going to say it's 1 atmosphere. And 0 degrees C, what phases can exist? Well, you can have, this is going to be on that line or at a point on the line between liquid and solid. So you can have both liquid and
solid together.
Ice and water.
Okay. If the temperature were any different or the pressure were any different, then you could only have one or the other, depending on which way you move. That's why I had in the first semester, if we wanted to know the melting point of water or the freezing point of water, we had ice and liquid water together, and you had to have both of them. Then at atmospheric pressure, they would be very close to zero. 20. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? Okay, what's the opposite of evaporation? Evaporation is going from liquid to gas. So what if we go the other direction? What's that mean? Condensation. Okay. So those have to be in equilibrium in a closed vessel to measure vapor pressure at any given temperature. All right, 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? So vapor pressure is that one physical property of a substance that runs opposite to intermolecular force. The stronger the intermolecular force, as it goes up, vapor pressure, let's see, vapor pressure goes down. Because as you increase the strength of attractions in the liquid phase, you get fewer of them into the vapor phase. So the pressure goes down. All right, so in order to have, which one of the followings would have the highest vapor pressure? Highest vapor pressure would have the lowest intermolecular force, just opposite. So if we look at those and see, based upon their boiling point temperatures, we want to look for the lowest boiling point. That will indicate the lowest force, which would be diethyl ether, wouldn't it? 34.5 degrees. That should give us the highest vapor pressure. The rest of the properties we studied are directly proportional to intermolecular forces. This is the one that runs counter. Which of the following decreases as the strength of attraction? Oh, we just talked about that. Vapor pressure. Okay. That happened. 23. Okay. In which of the following processes will energy be evolved as heat? Okay. So this is where I draw my triangle. I'm going to put gas up here. I'll put liquid over here and solid over here. So if we're going from liquid to solid, that is, well, the proper term is fusion, but we can call it freezing. Liquid to solid is freezing. And the opposite, if we go the other direction, that's melting. Okay. If we go solid to gas, that's sublimation. If we go gas to solid, that's deposition. Then if we go, let's see, liquid to gas, that's vaporization, or, yeah, that's a good term. vaporization. We go from gas to liquid. That's I'm missing one. Condensation. Okay, now in terms of heat, the enthalpy of whatever it happens to be. If we're in order to go from a gas to a liquid or a gas to a solid, we've got to remove heat from it to give the intermolecular forces a chance to attract them. So if we go from go condensation, or we go deposition, or we go freezing, these three, the delta H should be negative. We're giving up heat. So the others, vaporization, we have to put energy in. Sublimation, solid to gas, we have to put energy in. And melting, we have to put energy in. So with that, which of the following will energy be evolved? So it's one of these in here: condensation, deposition, or freezing. Melting, vaporization. Oh, I left one out: crystallization. Well, this is phase change. Crystallization is it's special. When we say crystallization, we're talking about going from individual ions to the solid. That's usually how we measure those forces. And this is definitely going to be a big negative. Yeah. Let's see, 23. And skip a few, 25. Okay, 25. In the interest of time, I'm not going to draw this one. We're just going to refer to the diagram. We've got the solid, liquid, gas phase lines in there. We can see the triple point. We've got a 1 atmosphere line going from low temperature to high temperature through solid, liquid, gas. All right, so this is not water. Notice that the solid liquid slope is positive. That's most substances. So which one of these statements is correct? The diagram is qualitatively correct for water. No. Because of the slope of that line, solid liquid line, phase line is a positive slope, water is a negative slope. The diagram shows that the melting point of the solid increases with increasing pressure. The melting point, we go from liquid to solid. The melting point increases with increasing pressure. So what that means is pressure is directly proportional to temperature, which means that slope is positive. That's true. So B is a true statement. Triple point is below 1 atmosphere, so C is false. And D, the diagram could represent the phase diagram of carbon dioxide. Not likely, because at 1 atmosphere pressure, you should be able to go from solid to gas. So we'd have to move that 1 atmosphere down lower, a lot lower, so that we could go from straight from solid to gas at 1 atmosphere. So that's not carbon dioxide either. All right. Oh, another one, 26. All right. Below is a phase diagram for compound Q.
you want to purify sample Q that was collected at 1 atmosphere pressure and 100 K. I might have to draw this one in order to talk about it. Okay, so this temperature in K goes 0, see 1, 2, 3, 4. How about that? That's 100 and this is 400. Oh, it only goes up to 300. Okay. All right. And then we've got half, 1, 1.5, 2. It only goes up to 1.5. Well, let's try that again. 1.5 is up here. So that means this is 1 and this is a half. And that's pressure in atmospheres. Okay. So now we've got the triple point is about here. And this one goes up like that. And then it goes like this. And then it goes down like that. Okay. So we want to purify a sample of Q that was collected at 1 atmosphere and 100 K. So at 1 atmosphere and 100 K, that's our starting point. That's where we collected the sample, but we want to purify it by subliming it. And that's a valid technique, separating impure mixtures. If we want to sublime it, we've got to go from solid to gas. So I think the best way is to bring that pressure down to here and then heat it up. Okay, so we would come down, say to here, and then go that way. So which one of those fits? Increase the pressure? No. Increase the temperature, keeping the pressure at 1. Keep it at 1, it's going to go through liquid. All right, so we got to decrease the pressure. C, lower the pressure to 1/2 atmosphere. Yeah, that's good. And then increase the temperature to 200. Yep, that'll do it. So C is your best answer. Got a bunch of phase diagrams in there. How about this one? Oh, we did that one already. Okay, we'll skip 29 and go to chapter 10, moderate difficulty. You know, we start renumbering, but we're still in chapter 10. Moderate. Okay, which of the following is the correct order of boiling points for KNO3, methanol, ethane, and neon? Correct order of boiling points. And it looks like the way they've got them ordered is lowest boiling point to the left, highest to the right. Well, the highest one is going to be this one, right? So I would go like that. The lowest one is going to be this one. We have to decide which one of these. Well, ethane is like this, right? If you drew out your Lewis structure, it would look like that. It's non-polar. But methanol is like this. Hydrogen bonding. So it's going to be more strongly attracted than this one. So this way, we would have, and if we put it in that order, then we'd have neon, then ethane, so C or D, and then D. D looks like the best one. Yep. Whenever I see a problem that says put these in order, I'll try to figure out the extremes. which one is absolutely this way and the other one's absolutely that way. Then I arrange the ones in the middle. That's just my logical approach. Okay, number 4. Assume 12,500 joules of energy is added to 2 moles or 36 grams of water as an ice sample at 0 degrees. Gives the molar heat of fusion, and I'll discuss that in a minute. Specific heat of water, the molar heat of fusion, vaporization is 40.6 kilojoules per mole. Resulting sample contains which of the following? Okay, if we're starting off with 12,500 joules of energy, then what phase changes are we going to go through? 2 moles of ice at 0 degrees. So if we look at it this way, as we add energy, then the temperature is going to increase gradually. That temperature is going to go up. And if we start at 0 degrees Celsius, then we're going to heat the ice up until we get, that's solid, until we get solid and liquid together. And it's going to stay, actually, that's not 0 degrees, that's less than 0. This is 0 degrees, sorry. Then we're going to heat, once we get to liquid, we're going to heat the liquid up until we get to 100 degrees. And then we're going to, let's see, liquid, then we're going to have liquid and gas together until we got all gas, all steam. Then we can heat the steam up further. Right, so then we got enough gas. Okay, so where do we start? We start at 0 degrees right here with an ice sample. So this is our starting point right here. We have 2 moles or 36 grams of water. 2 moles or 36 grams of water at 0 degrees C. Okay, what do we have to do first? We've got to add enough energy to melt all of that. So the formula for that references the molar heat of fusion. How much heat does it take to melt 36 grams or 2 moles? Well, it's in terms of kilojoules per mole. So here we have 2 moles of water, right? 2 moles times 6.02 kilojoules per mole of water. And that's the amount of heat it takes to convert all of that water into liquid. So we're going to get to this point with fusion, the heat of fusion. All right, so let me get my calculator out. And this is, well, I don't need my calculator. This is 12.04 kilojoules, or 12,040 joules, right? Okay, so we've used up that much, 12,040. What do we have left? 0, 6, 4. 460 joules are left. Now what we're going to do is heat up the water, right? And remember the temperature change is equal to the specific heat of water, that's our K, times, wait a minute, times temperature, times change in temperature. This is the change in energy, right? Let me see if that makes sense. Specific heat is joules per gram degree C. We need to know the mass and the temperature change. I knew I was leaving something out. Okay, so we have a value here that's 4.18 joules per gram degree C. Right? Change in temperatures are unknown. We want to know how far do we get from here to here on that scale. Now, if we go all the way, if we can change the temperature by 100 degrees or more, if we can go 100 here, that means we've reached we've started boiling. And then the mass is 36 grams. Right? But we also have 460 joules as the amount of heat that's available. So now if we solve for delta T, then we divide 460 by 4.18 and then divide it by 36. And this is 3.1 degrees C. So we've only moved from here 3.1 degrees C. Right. We've still got liquid. That's it. Just liquid and nothing else. Only water, only liquid water. Okay. Now, let's see, scroll. Oh, we're going to go to difficult. Right. Number one. All right, a crystal was analyzed with X-rays having 2.33 angstrom wavelength. The angle of the first order diffraction was 19.2 degrees. What would be the angle for the second order diffraction? All right, here we have to go to, let's see, useful information. We need Bragg's equation. N lambda equals 2d sine theta. Plus 2d sine theta. Do better than that. Okay. So what we've got is, what is the constant for this crystal? What does not change, right? We can change the order. We can change the wavelength. Well, the wavelength doesn't change, so that's one of them. Right? Our wavelength is constant. Theta will change if we change this one, but distance between the layers, that is fixed also. Okay. So we have two approaches, and I've found usually my students are able to follow me if I break the problem into two steps. One, we want to find out what D is. What's the distance between the layers? So in order to do that, right, step one is we take this formula and plug in what we know. Right? N equals 1. Lambda, we can use, if we use angstroms here, that's going to be in angstroms too, which is okay. 2.33 angstrom wavelength. You know what an angstrom is? We haven't talked about that. An angstrom, 1 angstrom is 10 to the minus 10th meters. All right, so it's 1 order of magnitude smaller than a nanometer. That used to be, and still is, a commonly used unit of measure. Okay, that's equal to 2 times this unknown distance times sine theta. What is theta? The angle, 19.2 degrees.
Okay? So D is going to be 2.33 angstroms. Right? We go over here, keep that one there. It says 2 on the bottom, and then sine 19.2 degrees. Okay, so your calculator will give you sine. Have you had trigonometry? Okay. So you really don't know what we mean by sine and tangent and cosine, all that. Okay. So just use your calculator. There's a key in here that's labeled sine. So I'm going to put in 19.2 and hit sine. And that value there is 0.3289. If I had time, I'd give you a crash course, but we don't have time. So this times 2 divided into 2.33 is the distance between the layers is 3.5425 angstroms. Okay. So now we can go to step 2. Step 2 says that now that we know the distance between the layers, we can make theta. This was like theta 1. This was theta 1. We want theta 2. What would be the angle if we were using n equals 2 instead of 1, second order? Okay. So now we're going to put 2 in here, and the distance between the layers, the wavelength is still the same. We didn't change that. Then we have, excuse me, yeah, 2. And then we have 2 here still, times the distance between the layers, which is 3.5425 angstroms, times sine theta. Okay. Now we're going to solve for theta. We need to know that angle. So we keep this on one side. And then we say 2 times 2.33 angstroms divided by 2, 3.5425 angstroms. So we get a dimensionless number, which is fine. It works out. 2's cancel. So 2.33 divided by 3.5425 is 0.6577. That's sine theta. In order to go backwards, we use the arc sine. So on your calculator, you have sine here, and then usually shift up to arc sine, a sine. So put that number, that number's already in there, so I just need to hit my function key and go a sine. And now theta is 41.1 degrees. That's the angle for the second order. So what that means is if we have intensity of the return signal as we're scanning through angles, then at if we have theta here, then at 19.2 degrees, we'll get a big peak. And then it'll go along, and when it gets to 41.1, we usually get a smaller peak. Okay. This is first order, this is second order. And you can get third, fourth, and fifth orders, but they usually get smaller and smaller in intensity. It's kind of like if you look and see a rainbow, sometimes you can see 2 or even 3 rainbows. So the really brightest one is the first order rainbow. The one that follows its track to one side is a little dimmer. That's second order. And then if you're lucky, you might get a third order at even dimmer. Okay. We could have combined both equations into one and then solved it all at one time, but I found that that's a little too much for most students. I mean, it's perfectly valid algebra,
but, you know, they're having a hard enough time with chemistry without having to complicate it with algebra too. 2. Okay, chromium metal crystallizes as a body-centered cubic lattice.
body-centered cubic is our chromium metal.
Body-centered cubic. If the atomic radius of chromium is 1.25 angstroms,
So the radius equals 1.25 angstroms.
if that's given, what's the density of chromium in grams per cubic centimeters?
So we're looking for the density in grams per cubic centimeter. So we need to know the mass and we need to know the volume. Okay, we're going to use the formula for body-centered cubic volume to tell us what the volume of the unit cell is. So this unit cell volume equals what for a body-centered cubic?
Let's look at our useful information. BCC, there it is. It's 4. Why is that A? It's 4R divided by square root of 3, isn't it? Number 2 difficult. Let me be sure. I could have made a mistake there with the with that formula. Be sure. Difficult. Here we go. Oops. I'm in the wrong chapter. Sorry. Oh, the equal sign is missing.
What we're saying is this unit cell volume is A in that formula. And that's
What was it again?
That's
4.
4R over square root of 3.
Yeah, there we go. So that's the volume that we would put in here. So we have, but this radius, if we want the units of volume to be in cubic centimeters, then we need this to be in centimeters. Right. So I'm going to do a chain conversion. 10 to the minus 10 angstroms is 1 meter. And then I can convert meters to centimeters. No, that's not right. This is not the volume. Unit cell edge. That's what the A means. That's the edge on the cube. I knew it didn't make sense. Because where's the cube in here? There's no cube. We have to do it later. Okay, so this is 1 meter equals 100 centimeters. Right. So let's get that value. 1.25. And if we divide by 10 to the minus 10, that's the same as multiplying by 10 to the 10th, isn't it? That doesn't make any sense. I'll tell you what. I like this is better. This is better. You're writing in pencil, aren't you?
Yes.
You know better than to use pen in this class. Let's do angstroms first. 1.25 angstroms. Square root of 3. That'll give us the radius. That'll give us the edge of our cube in angstroms. So that's 1.25 times 4, and then square root of 3 divided into that. So this is 0.5556 angstroms. Okay, so now the volume is equal to the A cubed, which is 0.5556. It's messy. 5556 angstroms cubed. Okay, so I enter that one, do this, do that, and this is 0.1715 cubic angstroms. Now we can convert it to cubic centimeters. Okay, so how do we do that? Well, we know that that was wrong. It's 10 to the 10th angstroms per 1 meter. Now it makes sense. Because angstrom is a smaller unit than meters, takes more of it. Yeah. That was my mistake. So, but we have cubic angstroms. Right? So I need to do this to get rid of that. Now I need to change to centimeters from meters. That's 10 squared. But that needs to be cubed too, because now we've cubed this one. That one has to be cubed. So this volume then is going to be this value divided by, I'm going to do, let's see, 1 exponent 10, enter, 3 times, okay? And then this is going to be 10 to the 6th, right? 2 times 3. 6 times. This is 1.7147. I did that wrong. I did that wrong. If I do 1 exponent 10, yeah,
So the unit cell edge where it's like 4R, when I did it, I could have done it wrong too, but
well, you got a different number.
Answer.
Okay.
2.886, and so it's
1.25 times 4, and then 3 square root divide. Yep, you're right. $2.8868, correct?
yes, that's what I got.
Okay, start over again. Okay. See, this one, I'm going to take the inverse of, let's see, enter 1 exponent to the 10th, and I'm going to do the inverse here, and then cube it. 3 there. This should be 1 times 10 to the minus 30. And this should be 10 to the 6th, right? 10 to the 6th times that. So those together are 1 times 10 to the minus 24 times this, well, which would be 2.8868 times 10 to the minus 24 cubic centimeters. .88 times 10 to the minus 24 cubic centimeters. All right. How many atoms of chromium does that represent? If it's a body-centered cubic, remember, body-centered cubic, then we've got these corners covered, but there's one in the middle. Remember, if we have the corners only represent 1 atom, then this one is 2 atoms. So this unit cell is representative of 2 atoms of chromium. So if we do 2 atoms, and we want to find out what's the mass of 2 atoms, because that's what goes in here. This is the volume of 2 atoms in that unit cell. So if we do 2 atoms, then we want to get rid of the atoms for moles, because we know that our conversion factor is molar mass. So let's see, 6.022 times 10 to the 23rd, 1 mole. Once we get moles, then we can do molar mass for chromium, which is 51. Actually, rounded off to 2 places is 52. There we go. So that'll give us the mass that would go in this formula. 2 and 6. 3 divide 52 times. This is 1.727 times 10 to the minus 22 grams. Okay. And let's see, I need to flip that and divide. The density then would be 59.8 grams per cubic centimeter. Is that right? No, it's not right. I made a mistake somewhere. Body centered cubic. That's right. Is the volume right? 10 to the minus 24. Okay, I'm off by a factor of. Let's do this again. Is this right?
That's what I
Came
got.
from here.
Yeah.
Yeah. Okay. Oh. Right.
My
No, wait a minute.
answer I got was
This is
like
the edge.
7.
Oh, okay. So this needs to be like that, because this is the edge, isn't it?
Yes.
Then we need to cube it. Okay, that's where I made my mistake.
And then from my whole answer that I got was like 7.185.
Mm-hmm. Yeah. 2.8868 cubed. This is cubed. 240575. Do that again. 2.8868. And then cube it. I got 24.075. And this is that correct? Yeah, because this becomes minus 10 times 3 is minus 30. That's right. This is meters. This is cubic meters, 6. 6. And 6 from 30 is minus 24. But there's 24. Okay. So this is actually 2.40575 times 10 to the minus 23. 40575. And that divides into, see, did I do this one right? I think I did that one right. And this is there. And this is 1.727 exponent times 22 divide. So this should be
7.18, right? Remind me never to take my own tests. Okay. Chapter 11 now. Got time? Got about an hour, don't we? An hour and. Do we? Oh, no, we got 45 minutes. All right, we're gonna have to move along. And this is the easy section. Number one. Okay. In a 0.1 molar solution of sodium chloride in water, which of the following will be closest to 0.1? 0.1 molar, 0.1 moles per, actually mole, per liter. So, excuse me, it's not likely to be mole fraction. Mass fraction shouldn't be it either. Mass percent, we could go through each one of these and work them out, and I'm sure I did in the problem set. But if we look at molality, that would be 0.1 mole per kilogram. This is of solution. This is of solvent. Now, is there a great deal of difference between these two? This is the same. Are these two about the same? With a concentration that low, kilogram of solvent is roughly a liter of water. So that's why 1 mole and 1 molar are almost the same. Okay. 2, which of the following concentration measures will change in value as the temperature of the solution changes? Anywhere you've got volume in the calculation will change, and that's molarity. Molality has nothing but mass and moles, numbers. Mole fraction is just numbers. Mass percent is mass, it won't change. So the one that will not change is, that will change is molarity. Which of the following chemical or physical changes is an endothermic process? Endothermic, we've got to put energy in to phase change. The evaporation of water, oh yeah. You change from a liquid to a gas, you got to put energy in. Combustion of gasoline is exothermic. Everybody knows that. When you mix a concentrated acid with water, it's always exothermic. If you mix, or if you mix a base, like sodium hydroxide pellets or flakes, and you mix them in water, it's going to get hot. So that's exothermic. Freezing of water, when water freezes, you're reducing its energy by going from liquid to solid so that the intermolecular forces can dominate and pull things together. So you have to give up energy. So that's exothermic. The only endothermic in there is the evaporation of water. Number 4. Which statement about hydrogen bonding is true? All right, hydrogen bonding is an intermolecular attractive force between 2 hydrogen atoms. No. The only way you can get them to attract each other is not by hydrogen bonding, but by covalent bonding. So A is false. B, the hydrogen bonding capabilities of water molecules cause 1, 2, 3, 4 butane to be more soluble in water than methanol. Wrong. It's the other way around. Hydrogen bonding is possible with methanol because it has oxygen bound to hydrogen. So that's false. C, hydrogen bonding of solvent molecules with a solute will not affect the solubility. That's false on its face. Hydrogen bonding does increase the solubility of, or can increase the solubility of a solute. D, hydrogen bonding interactions between molecules are stronger than the covalent bonds. If that were true, what would happen? Molecules get ripped apart, right? If your intermolecular forces are stronger than the intramolecular bonding, then you cannot have molecules. They will get torn apart by the external forces. So E is by process of elimination. E should be true. Hydrogen bonding arises from the dipole moment created by unequal sharing of electrons within certain covalent bonds within a molecule. That is true. And those certain bonds are with oxygen, nitrogen, fluorine. Five. Which of the following favors the solubility of an ionic solid in a liquid solvent? Well, let's see. The large magnitude of the solvation energy of the ions. Remember the solvation energy, where we have, say, ions in the solid, and then we've got water molecules coming in from all sides. And they're plucking these ions off. Solvation energy is the amount of energy given up when you remove those from the crystal. So the large magnitude of solvation energy of the ions favors the solubility of an ionic solid in the solvent. The small magnitude of the lattice energy for the solute. If the lattice energy is small, what does that mean? Well, for this one, gas, lattice energy would produce this solid. If this is a small value, right, it's going to be negative. If it's a very small value, then what are the forces holding these things together? Big or small? If this is a small negative, then the amount of energy required to break that crystal up is very, very small. So if there's a small magnitude of lattice energy, then that will also favor solubility. And C, a large polarity of the solvent. If it's ionic, then you're going to have polar molecules orienting themselves to the ions of the ionic solid. And that large polarity will work well to extract ions from the crystal. So all of those are true statements. Let's see. This one's going to take a while to work. I'm going to hold this one. Let's see. Chapter 11. And this is not easy, but it's in the easy section. Number 6. If we have time, we'll come back to it because it's very involved. We'll try to get the rest of them out of the way and come back to it if we can. If we can't, then I've worked it out in detail in the worked problems. Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the following questions. So we got this piston, and we have a gaseous solute being dissolved in the liquid. So what happens? Which of these statements is true when the piston is pushed down? When you push the piston down, what does that do for the available space for those gas molecules? It decreases them. Now, are we changing their kinetic energy? No, we're not. But with the same velocities, average velocity that those molecules have, their impact against the surface of the liquid is more frequent because we've decreased their volume, which means they're going to be more soluble. More impacts means more solubility. So this will cause the pressure of the gas to increase? Yes. And the concentration of the dissolved gas to go up. And the best one for that is C. That's Henry's law. 8. Which of the following correctly states the relationship between temperature and solubility of a substance in water? Well, we know that as the temperature goes up, solids become more soluble. Most become more soluble. Some become less soluble. Okay? As the temperature goes up for gases, their solubility always goes down. So let's see, the best one here, solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That's true. It has to do with the ability of water to solvate the ions of that substance. And that's as far as I can go. There's really, I don't know of any theory that accurately predicts solubility. We can say some things about what we think is happening, but we don't have a theory that can predict quantitatively what their solubility is. A solution contains 1 mole of liquid A, 3 moles of liquid B. Okay, so we got this solution here. Got 1 mole of A and 3 moles of B. 3 moles of B. 3 moles of B. Okay. The solution has a vapor pressure of 314 torr. That's measured vapor pressure at 25 degrees. The pure liquid, A, has a vapor pressure of 265 torr, and B has a vapor pressure of 355 torr at the same temperature. Which of the following is true? Okay. What we're saying is both of these are volatile to a lesser or greater degree. So we've got a Rayleigh law that is modified to incorporate both of them. All right. If we say 314 torr is measured, then it will have to be equal to the mole fraction of A times its vapor pressure of A under pure conditions, plus the mole fraction of B times its pure vapor pressure. Okay. If it's ideal, then this calculation should yield that value. Okay, so what's the mole fraction of A? Well, there's a total of 4, so 1 over 4 is 0.25. 0.25 times its pure vapor pressure of A, which was 265, right? 265 torr. How about B? Well, it'd have to be 0.75.
Since there are only two components, they have to add up to one.
And its pure vapor pressure is 355.
Okay, so let's see what this value is and compare it with this value. Because we don't know if they're equal yet.
0.25 and 265 is 66.25. And 0.75 times 355 is 266.25. Add those together and we get 332.5 torr. This would be ideal if there's no interaction between the two. But we actually get 314, which is less. So what does that say about the way A and B interact? They attract one another. If they didn't attract one another, then we should have this ideal value. But since they attract one another, they impede their vaporization, which is why we have a lower value. Okay, so which one of these statements fits that one? This solution exhibits a negative deviation from Raoult's law. That B is true. It's a negative deviation because this is less than that.
And if we drew the, let's see, increasing A this way, increasing B this way.
So A has a 265. Pure A has 265. Pure B has 355. It's up here somewhere.
Okay. So ideal, we would go like this and like this. And ideal would be like that. Right? But when we say 75% A, so it's about right here. Right there. And this value that we measured is right here, not right there. So we get a negative deviation. Okay. A cucumber is placed in a concentrated salt solution. What will most likely happen? This is a question about osmotic pressure. So if we have a cucumber, slice of cucumber here, and we put it in saturated sodium chloride, what's most likely the difference between dissolved solid concentration? It's probably higher outside the cell, isn't it? So that means water is going to go that way. And the cucumber should shrink. Water will flow from the cucumber to the solution. That means the solution was hypertonic to the cucumber. A, yes, no, that's the answer. 13. Osmotic pressure depends on all but which of the following? Well, let's see. The formula is osmotic pressure is equal to molarity, right, times gas constant times temperature. And if the dissolved substance breaks up into pieces, then we need a correction factor. Okay, so it's dependent on which? Molarity, B is true. Temperature, C is true. Ratio of moles of solute to salt, that's the same as molarity. And the one that's not dependent upon is pressure. Atmospheric pressure is not in that formula. So A is the outlier, the bad one. Okay. 14.
Shaving cream is an example of which colloid type? Well, let's see. What do we have? We have gas in a liquid, right? Gas in a liquid. That's a foam. That's a foam. If we have a gas in a solid, it's a solid foam. If we have, let's see, liquid in a liquid, that would be an emulsion. If we have a solid in a liquid, that should be a sol. An aerosol, if we have a solid, actually a liquid in a gas, it's an aerosol. And if we have a solid in a gas, it's a solid aerosol. Coagulate is not a colloid type. That's what happens when you destroy the colloid. You coagulate. And because colloids are based upon particle size. The particles of the suspended medium must be small enough, that means low enough mass, so that the kinetic energy of the suspending medium is sufficient to knock them up and keep them suspended. So particle size is the key to colloids. Okay, moderate. Right. Scroll down till we find one. Here we go. Number 3. A 0.2 molar solution of a solute X in benzene displays an osmotic pressure given by the formula 0.1 times RT, which is the following most likely is the case. All right. If we have a 0.2 molar solution of, what do we call it? X in benzene. Okay. And we measure the osmotic pressure. We find out what this is. And that's equal to this 0.1 times RT. So what does that 0.1 incorporate? Well, it has the molarity plus the I, or times the I. So if this is 0.1 equals I times molarity, but the molarity is 0.2, right? So 0.2. What does I have to be? I has to be a half, right? So what do we say? If it's positive, that means the substance is breaking up into pieces. But if it's less than 1, that means we're getting dimerization of X. X2 is in solution. We're taking this concentration and reducing it by half. So the only way you can do that is to combine X's into these associations. Right? So X exists in benzene as X2. I think the reason I threw that in there is because we tend to think of I as always a positive number. We sort of alluded to it when you get positive numbers for I. Then if you increase the concentration so high, then you start to get ion pairing again. Ion pairing will reduce that value, that whole number, by some fraction. So this is the extreme. Okay, number 4. Which of the solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molal calcium chloride would have the highest vapor pressure, lowest boiling point? So we had 0.1 molal sodium chloride. We have glucose, 0.15 molal glucose, and 0.1 molal calcium chloride. Okay.
This one is vapor pressure. Let's see, Roman numeral 1 and 2 is boiling point. We want what? The highest vapor pressure and the lowest boiling point. Out of this group, which one would have the highest vapor pressure? Well, vapor pressure is dependent upon the, well, these are not volatile, right? So we're talking about simple Rayo's law. So whatever they're dissolved in, which is probably water. So what would the effect of these have on the vapor pressure of water? Well, as we add these things to water, it's going to decrease the water's vapor pressure. But which one decreases it the least? The one that has the least concentration. This is 0.1 molat, right? Which is what in terms of the I? It's the I equals 2 here, right? I equals 1 there because glucose doesn't dissociate. And this one would be 3. So the observed concentration here would be 0.2, 0.15, and 0.3. So the least effect on vapor pressure, let's see, what is it? Highest vapor pressure, yes. The least effect on vapor pressure would be glucose. Right? So this one would be the least vapor pressure. How about the lowest boiling point? The lowest boiling point is going to have the highest concentration. Excuse me. No, boiling point elevation. So what we want is the least effect on the boiling point of water, which would again be this one. So both of them give you that result. I mean, this one gives you the results you want. That's D. Okay. 5. What does 5 talk about? This is the same array, lowest vapor pressure. Okay, now we've got lowest vapor pressure and the lowest boiling point. All right, so we still got this one for the lowest boiling point. But the lowest vapor pressure is going to be this one. The highest concentration will give you the lowest vapor pressure. So that would be calcium chloride and glucose. Right. We got it difficult. Number 2. So I got 20 minutes. How many more do I have? Let me see. Solution prepared, non-volatile, solute, vapor pressure of the solution is 60. Is 132. Vapor pressure of water. What's the molar mass of the solute? All right, I'm going to hold that one too. This is difficult too. We'll have to come back to it because that's going to take some effort. And I want to be sure to get through all of them. You have table sugar and table salt. 4 is going to be another involved one. So we'll come back to that one. Okay. So let's go back to 2. Okay. So number 2 here is asking for the molar mass of the solute.
Yeah, molar mass of the solid. So in order to do that, we need mass and moles. Okay, we have the mass, 53.8 grams. We got the mass. We need the moles. How many moles does that represent? Okay, the information we're given is 85 grams of water. This is dissolved in 85 grams of water. So the solvent equals 85 grams of water. The vapor pressure of the solution at 60 degrees is 132 torr. So the solution, pressure of the solution equals 132 torr. Yeah, 132 torr at 60 degrees. Okay. The vapor pressure of water at 60 degrees is 150 torr. So the vapor pressure of water, well, actually it's not standard conditions, it's the vapor pressure of water is 150 torr at the same temperature. Okay. So we're dissolving a non-volatile solute in water. And what we want is to find the number of moles, 85 grams. Yeah, the number of moles here of that solute. Okay, we know that the vapor pressure is going to be reduced. So the pressure of the solution is given at 132 torr. And that's equal to the mole fraction of water times its vapor pressure, pure vapor pressure. And and this is 150 torr. Okay, so from this formula, we can get the mole fraction of water. So what would the mole fraction of that solute be? Be 1 minus that. Okay, so the mole fraction of water would be 132 divided by 150. Mole fraction of water equals 0.88. The mole fraction of the solute equals 0.12. Okay. Let's see. That doesn't help me much, does it? Okay. I know where to go now. We know the mass of the water. How many moles is that mass? Grams, moles. 18.02. Divided into 85. Okay. That's 4.717. 4.717 moles of water. Okay. So if that's the total moles of water, and this is the fraction, so what's the total moles of the solution? Total moles of the solution would be 0.88 divided into 4.717. If the mole fraction of water, let's do it this way. The mole fraction of water equals moles of water per total moles, right? Okay. We know the moles of water is 4.717, and we know the mole fraction of water is 0.88. So the total moles is 4717 divided by 0.88. Right, total moles. Yep. So that's 5.3602. The mole fraction of the solute is 0.12 of that total. Which is 0.6432 moles. That's what goes up here. Dilution. Pretty good. Okay. We're going to divide that into 53.8. And we get 83.6 grams per mole. Okay. So I got 10 more minutes. Which one of these do I want to do? Got that one. I think this one is this one's a bonding energy problem, I believe. Go back to, let's see, is it easy 6? It's not really easy. I don't know why it's in this group. Yeah. What we're trying to find is which salt forms a stronger attraction with water. So we're comparing the two. And the other one, 4, at the end. Or this one. No, that's not it. It's this one. This one is an algebra problem in the extreme. Let's do 6. Yeah, let's do 6. 6. I can remember the steps. Okay, we've got 2 solid salts, potassium fluoride and rubidium fluoride. And potassium and rubidium are alkali metals. Potassium fluoride and rubidium fluoride solids. Okay. The lattice energy is given for Kf as -804. And the heat of solution is -15 kilojoules per mole. Rubidium is a little bit less lattice energy, and that makes sense. Rubidium's a bigger ion, right? It can't get as close to fluorine as potassium can. So it's going to have a lower, a smaller value for lattice energy. But the heat of solution is -24. It gives up more energy when it goes into solution. So which salt forms stronger attraction with water? All right, when we think of what happens when they go into solution, right? The total heat of solution can be broken down into this first one, which is the lattice energy. You break it up. Lattice energy. How much energy does it take to break it apart? Right. So this is an endothermic process. So whatever value we have for lattice energy, we need to change the sign, because lattice is an exothermic, and we're going to break it apart. We need to put energy in. Okay. So once we get these apart, by putting that energy in, then we also have to make a hole in the water. Right? We got to break the water apart so that it can do its thing and consolidate these guys. So that's endothermic also. Then we solvate, right? The heat of solvation. Yeah. Okay. So this would be an approach for each one of those. Well, we're given the heat of solution for each one, right? We're given the lattice energy for each one. Let's do that one first. So the lattice energy for this one is equal to minus 804 kilojoules. And the lattice energy for this one is equal to minus 768 kilojoules per mole. Okay. That's this part right here. Then we're given heat of solution. So heat of solution is this combination right here. How much energy does it take to make the whole, and how much energy do you get back when you solvate them? So this whole term here is heat of solution. Okay, so this is exothermic, this is endothermic. So if you get a lot of energy back, then this heat of solution is going to be negative. If you don't get much back, then it's going to be positive. Okay, so the heats of solution were both negative. That means we get some energy back. So for KF, it's minus 15. So KF minus 15 kilojoules per mole. And rubidium chloride, let's see, yeah, heat of solution, delta H solution is that. And over here, delta H of solution is equal to minus 24. Okay, if we're comparing the attraction of these different compounds to water, we're looking at this term right here. Which one of these gives up more energy than the other one? Well, that's not right. Because we could do a direct comparison. No, this is heat of solution. I'm sorry. This is heat of solution. This is just a combination of those two. I'm sorry. Yeah. These values go in here and here. So this delta H is a combination of these two. Well, this one's going to be the same for both of them, right? Because it's the same for water. So if we get this value, we know the difference is due to that one. And that's what we're after right there. Okay. All right. So this lattice energy, since it's endothermic now, we have to make it positive. So this calculation for KF is going to be minus 15. I'm going to leave the units out. Equals, and this was going to be positive 804 plus that delta H right there. So this delta H is equal to minus 819. Yeah, it's negative on this side. That makes it minus 18 kilojoules per mole. And on this side, the delta H is going to be minus 24. Actually, minus 24 equals positive 768 plus that delta H right there. Okay, So this delta H is going to be, let's see, 2, 8, 9, 792, minus 792 kilojoules. Okay. So we can compare these two. This one is a greater exothermic process than that one. So the strength of attraction is due to this value, and that Kf is a stronger attractor for water. Now, if we look at the answers, Kf, since it has a larger lattice energy, that's not the whole story. Right? It is Kf, yes, but it's not A, it's C, since it has a more negative heat of hydration. That's the term here, hydration. No, heat of hydration is here. But we know it has a greater heat of hydration because this is the same for both of them. So when we compare those two numbers, it has to be due to this value. Okay. Yep, I got 1 minute. So we're going to have to leave number 4 out of the discussion. And hopefully you can look at number 4. Let's see. Let me see what I've got going. I'm supposed to have a meeting at some time. Let me see how much time I got. I might be able to do it. Come on. Go. Oh, not till 12:30. We can do the other one. You want to do the other one? Okay. That'd be number 4. 6 easy. 4 difficult, I think. Yes. Starting to give out on me. Okay. Excuse me. It's down. It's down. There it is. Okay. So we have a sample of a mixture of sucrose, table sugar, and table salt. And that total mass of that mixture is 10.4 grams. So the mass total equals 10.40 grams of the mixture. And that's a mixture of sucrose plus sodium chloride. Okay. What we're after is the percentage by mass of sugar. That's the question. We want to know percent mass of sugar, sucrose. And let's be consistent. They're saying sugar, that's fine. That's the question. Okay, the other information that we're given, when the mixture is dissolved in 150 grams of water, mass of water equals 150 grams. Okay. The freezing point is found to be minus 2.24 degrees C. So the freezing point of this mixture is minus 2.24. Okay, that's all the given information. All right, here's what we're going to have to do. we're gonna have to let X be the mass of sugar. So that if we find out what X is, we can ratio it to this total and find the percent. Okay. So we're going to let X equal mass of sugar. And then the X, 10.4 minus X equals the mass of sodium chloride. Okay. So if we're going to use the freezing point depression formula for our solution, then we know that the change in temperature is going to be equal to some factor I times the freezing point depression for water, depression constant for water, times the molality of the solution. Okay, here's the problem. This I is 1, this I is 2. Okay, so this is the trick. This delta T then is due to two things going on. The I for sugar, same K, times the molality of the sugar, plus, it's a linear combination, the I for the sodium chloride times the same K times the molality of the sodium chloride. Okay. All right. We know what the change in temperature is, 2.24 degrees. We know what the K is. Well, it wasn't given, so I have to look it up. Let me just go to this and see. Difficult 4. Difficult. That value is 1.86. So this value here is 1.86 degrees C per molality. We know that value. We know that I here is going to be 1, and I here is going to be 2. Okay. And we know this value is 2.24. Okay. So what we have to do, we need an expression for molality where we only have one unknown. So let's convert these terms to moles. Right. This one, X, moles of sugar, then will be the mass of the sugar times, let's see, this is grams per mole. So if whatever the sugar molar mass is it given? No, we have to calculate it. Okay. 12 pounds carbon. And then 22 hydrogens. Yep. 22 times 1.01. And then 11 oxygens. 16. All right. So that's 12.01 times 12. And then 1.01 times 2, add that in. And 16 times 11, add that in. 342.34 grams per mole. Okay. So this is 342.34. That's moles of sugar. And moles of sodium chloride would be 10.40 minus X. This is 1 mole. And sodium chloride would be, sodium is 23, and chlorine is 35.45. Yeah, 35.45. So that's 58.45 grams per mole. So that's the moles of each one. All right. If we calculate the molality, we just need to divide each one of these by here, kilograms. Right? So if we divide this expression by 0.15, it would just be another factor out here. Right? So there we go. Those are the moles. Actually, this is molality now. This is molality. Like that. Yeah, there we go. So this is the expression for the molality of sugar, and this is the expression for the molality of sodium chloride. And notice when we substitute these in there, there's only one unknown. That's X. That's what we want. So let's see if we can put these all together. So this is 2.24 equals, and that molality then is 1.86. And this term is going to be sugar. It's going to be X divided by 342.34 times 0.150. And this is going to be, wait a minute. Yeah, that's 1. Right. So there's a 1 in there that I left out. This one has a 2 here and a 1.86. And then times, I'm going to put it down here, is 10.40 minus X over 58.45 times 0.150. There we go. So that'll give us X. And then we can ratio X to this value and find out what its percent is. Let's see if I can do this. I'm going to take this term and this term and make it a factor of X. And do that first. So 1.86 divided by 342.34 divided by 1.15. And this is 0.0362X. And then this term is a little more complicated. I want to take these two, divide them into that term, times this one first. 1.86, 2 times 58.45, divide and 0.145. So this is 0.4243 times 10.4 minus X. So I now need to distribute this one. 10.4 times that value. So this is 2.24 0.0362X plus 4.4127 minus 0.4243X. There we go. So far, if I did my calculations correctly. So we need to get the x's on one side and the non-x's on the other side. So let's bring, if we combine these two, 0.0362 and minus 0.4243, that's a minus 0. Yeah, let's be consistent. 24. This is a minus 0.3881. Oops. Nope. Yeah, it is. That's times x. Excuse me. We can go ahead and bring this one over. That'd be a minus 4.4127. This one. 2.24 and then 27 minus. So this is minus 2.1727 equals minus 0.3881 x. Yeah. Yeah, that's right. So x would simply be this one divided by that number right there, because the negatives cancel. So split that by 5.593 grams. And that's the mass of sugar. Okay. So percent sugar is equal to 5.5983 divided by 10.40 times 1,000. And I get 53.8%. Of this. Rounding error, at a 53.9. Okay. The trick to this whole problem is very straightforward, except for that step right there, where we split these out. That if you can get that in your head, then the rest of it is just is very straightforward, followed by number crunching. And as usual, I went back and forth. So there's no logic to flow on the board. You had to be there. Okay. That's all I have or reviewed, unless something else popped into your head while we were doing this. Otherwise, Thursday we'll take this exam. And let's see, I think I have scheduled getting into chapter 12. Yeah. I'm going to do a lab notebook check. And then exam on these two chapters, and then lecture on chapter 12. I should be able to get chapter 12 done because there's no lab. I can bleed over into the lab.